It doesn't look dangerous at first. From a distance, it appears like any other moon, small, distant, orbiting quietly in the shadow of something much larger. But that illusion doesn't last long, because the moment you look closer, everything changes. The surface is not stable. It is not silent. It is not even solid in the way we understand it. It is constantly being torn apart and rebuilt at the same time. This is Io, and it is the most violent world in the entire solar system. Io doesn't just have volcanoes. It is covered in them. Hundreds of active volcanic centers, some erupting at any given moment, plumes rising hundreds of kilometers above the surface, lava flows spreading across vast distances, constantly reshaping the terrain. No other world we've ever observed behaves like this. Even Earth, with all its tectonic activity, cannot compare. Because Io is not just active, it is unstable by design. For a long time, moons were expected to be simple. Cold, inactive, geologically dead, leftover fragments orbiting larger planets. Io destroyed that assumption completely. What was once considered unreachable darkness became a real place of exploration, discovery, and possibility, proving that humanity can succeed even in the most hostile environments. NASA's Artemis plan. NASA's Artemis program is humanity's bold plan to return to the moon, this time not just for brief visits, but to establish a sustained presence. The program aims to land the first woman and the next man on the lunar surface, with long-term goals of building infrastructure that could support future explorers for weeks, months, and eventually years. Artemis represents a shift from exploration for curiosity to exploration for habitation, science, and preparation for missions to Mars. The South Pole was chosen as the primary target for Artemis missions because of its unique combination of sunlight and resources. Some crater rims receive near-constant sunlight, ideal for solar power, while permanently shadowed regions contain water ice that could be mined for drinking water, oxygen, and fuel. This dual advantage makes the South Pole the most practical location for a long-term human base and positions it as the gateway to deeper space exploration. Astronauts landing here will face extreme challenges. Temperatures in shadowed craters can drop to nearly -230 degrees Celsius, and the terrain is jagged, steep, and unforgiving. Communication will be difficult in deep craters where Earth is barely visible. Every movement must be carefully planned. One misstep could end a mission. They will rely on advanced suits, autonomous rovers, and real-time monitoring from mission control. Yet the Moon's South Pole remains a place where human life has never existed. Despite the technology, preparation, and planning, Artemis will place humans in one of the most extreme environments ever attempted. It is a place of cold, darkness, and silence. And yet, it is here, in these frozen shadows and sunlit rims, that humanity will attempt something unprecedented. But humans have never stayed here. No aliens, no myths. Despite the dramatic headlines and videos claiming secret bases or alien structures at the Moon's South Pole, the reality is far more grounded in science. No evidence exists of artificial formations, no signals from extraterrestrial civilizations, and no signs of technology beyond what humans have placed there. The craters and ridges are entirely natural, shaped by billions of years of impacts and geological processes. So why do so many sources talk about mysteries or dangerous secrets? The answer lies in human fascination. Headlines use suspense and drama to capture attention, but the true intrigue is scientific. These craters are mysterious not because of aliens, but because of time itself. Some areas have been in darkness for billions of years, preserving ice, rocks, and other materials exactly as they were when they formed. This makes them invaluable for understanding the Moon's history and the early solar system. The real mystery is survival. Water ice has persisted in these shadowed craters despite harsh radiation, extreme cold, and billions of years of exposure to space. Human spacecraft and explorers face real danger in this environment, and understanding how materials, technology, and possibly life support systems can survive here is what drives research. The South Pole's allure is not science fiction. It is the ultimate natural laboratory, offering insight into time, preservation, and the boundaries of human exploration. The Moon's South Pole is a place of extremes. Darkness stretches farther than the eye can see. Temperatures drop to levels colder than any natural environment on Earth, and the terrain challenges even the most advanced technology. It is a place that has tested spacecraft, confounded engineers, and captured the imagination of scientists for decades. And yet, standing in its frozen shadows, The danger begins to transform into opportunity. Where shadows fall, water ice endures. Where sunlight never reaches, history is preserved. Every jagged crater, every hidden valley, is a potential treasure trove of resources and knowledge. The very conditions that make this region deadly are the same that make it invaluable. For the first time, humanity sees the possibility of living off this world, of turning a forbidding landscape into a stepping stone for future exploration. The South Pole is the coldest, the darkest, and perhaps the most scientifically valuable place humans have ever attempted to explore. Its frozen craters hold water that could sustain life, provide fuel, and open the door to journeys far beyond the moon. Spacecraft and astronauts may falter, missions may fail, and yet each challenge teaches us something new, preparing us for the day we will stay longer, venture further, and explore deeper. This is not a place of myths or alien secrets. It is a place of physics, geology, and survival, a harsh teacher that demands respect and ingenuity. And within its eternal shadows lies the potential to change the future of space exploration forever. The moon's south pole reminds us that the greatest risks often hold the greatest rewards. It is both a warning and an invitation, a place where danger and opportunity coexist in equal measure. The most dangerous place may decide humanity's future. There could be a subsurface ocean, not vast like Earth's oceans, not exposed, but real, a layer of liquid water trapped beneath kilometers of ice. And if that was true, then everything about those fractures changed. Because cracks like that don't form randomly, they form under pressure. Inside Dione, heat generated by tidal forces, the constant gravitational pull from Saturn, could slowly warm its interior, not enough to melt the entire moon, but enough to keep pockets of water in a liquid state. As that water shifted, expanded, moved beneath the crust, it created stress. Pressure building over time, with nowhere to go, until the surface finally gave way. The fractures we see today may be the result of that release, the moment when internal pressure became too great and the crust split open. Not explosively, not violently, but gradually, over time, stretching, cracking, reshaping the surface from within. But that wasn't the most surprising part, because Cassini didn't just detect signs of an ocean, it detected something else. Charged particles surrounding Dione behaved in a way that suggested interaction with material escaping from the moon. Not large plumes like those on Enceladus, but subtle, almost invisible, as if something was leaking, slowly, silently, from beneath the surface. This raised a question that no one had seriously considered before. What if Dione is not completely inactive? What if those fractures are not just ancient scars, but part of an ongoing process? The evidence wasn't definitive. There were no massive geysers, no dramatic eruptions captured in images, but the signs were there, subtle, hidden, easy to overlook, and yet impossible to ignore once seen. A frozen world that refuses to stay still. Dione challenges a basic assumption about the solar system. That small world cool down and die, that over time they become inactive, geologically silent, frozen forever. But Dione doesn't fit that pattern. Its surface tells a story of movement, of stress, of change, and its interior may still be evolving. If Dione does contain a subsurface ocean, even a partial one, it places the moon into a category once thought rare. Ocean worlds, places where liquid water exists beyond Earth, places where the conditions for life might exist. That doesn't mean life is there. There is no direct evidence of that. But it means something important. The outer solar system is not as dead as it once seemed. Moons once dismissed as frozen relics are now being reconsidered as active systems, dynamic, complex, and still changing. And yet, even with all this new understanding, there is still something about Dione that doesn't fully make sense. Because the fractures are not evenly distributed. They appear in specific regions, aligned in ways that suggest deeper structural forces at work, forces we don't yet fully understand. Some of these fractures cut across older terrain, ignoring existing features as if they were formed under completely different conditions. Others seem to follow patterns that hint at internal layering, boundaries beneath the surface, guiding where the crust would break. This suggests that Dione's interior is not uniform, not simple, but structured, layered, and possibly still shifting, which leads to a more unsettling possibility. The cracks we see today may not be the final state of the moon. They may be part of a process that is still unfolding, because if there is still movement beneath the surface, if pressure is still building, then Dione may not be finished changing. And if that's true, then what we're seeing now is only a snapshot, a moment in a much longer story. But that's not the part that concerns scientists the most, because recent analysis suggests something even more unexpected. something that connects Dione to a much larger system, a system of forces that extends beyond a single moon and into the entire Saturnian system itself, because the cracks on Dione may not have formed in isolation. They may be part of something bigger, something that links multiple moons together through gravity, through resonance, through forces we are only beginning to understand. And if that connection is real, then Dione is not just a cracked moon, it is part of a chain reaction, a system of interactions that could reshape how we understand not just Saturn's moons, but how entire planetary systems evolve over time. But to understand that, we have to look beyond Dione itself. We have to look at the forces acting on it and what they reveal about the hidden dynamics of Saturn's orbiting worlds. Because the real story of those fractures doesn't end on the surface. It begins deep below it and continues far beyond it. Dione does not exist alone. It moves within a system of constant influence, a gravitational web dominated by Saturn and shared with other moons, each one tugging, pulling, and reshaping the others over time. What looks like a quiet orbit is anything but still. Every revolution around Saturn slightly stretches Dione, not enough to see, but enough to matter. This process is known as tidal forcing. Saturn's immense gravity pulls on Dione unevenly, stretching its interior just enough to generate heat. And that heat is the key. For a long time, scientists believed Dione was too small to maintain internal energy, that whatever heat it once had would have dissipated billions of years ago. But Cassini's data suggested otherwise. Dione is still being warmed, slowly, continuously, from the inside out. The resonance that changed everything. The situation becomes even more complex when you consider Dione's relationship with other moons. It shares a gravitational connection with Enceladus, a moon that is far more obviously active. Enceladus erupts with massive plumes of water vapor, driven by intense internal heating, and part of that energy comes from orbital resonance. Resonance occurs when two orbiting bodies influence each other's motion in a repeating pattern. In this case, Dione and Enceladus are locked in such a relationship. Each time Dione completes one orbit, Enceladus completes two. This consistent gravitational interaction prevents their orbits from stabilizing into perfect circles. Instead, they remain slightly elliptical. That slight irregularity is enough to keep tidal forces active, enough to generate heat, enough to keep internal structures from freezing completely solid. For Enceladus, this energy manifests dramatically, with geysers erupting into space. But for Dione, the effects are quieter, more subtle, more hidden. Instead of explosive activity, the energy is distributed through the interior, building pressure slowly, shifting layers beneath the surface, and eventually breaking through. The crust that couldn't hold. The fractures on Dione are not random damage. They are stress lines, evidence of a crust that was pushed beyond its limits. As internal heat caused materials beneath the surface to expand and move, the rigid outer shell began to stretch. Ice, though solid, can deform under enough pressure. It can bend slowly until it finally cracks. Those bright fractures we see today are the result of that process. When the crust split, fresher ice from below was exposed. Cleaner, brighter, untouched by space weathering. That is why the fractures appear so striking, so different from the darker, older terrain around them. They are younger, not ancient scars, but relatively recent features in geological terms. And that realization changes everything, because it means Dione has not been inactive for billions of years. It has been evolving, a system of connected worlds. What happens on Dione cannot be separated from what happens on other moons. The Saturnian system is interconnected. Energy is transferred through gravitational interactions. Orbital resonances maintain motion. Tidal forces distribute heat across multiple bodies. Dione, Enceladus, and even other moons like Tethys exist within this shared environment. Changes in one can influence the others. This means that Dione's fractures are not just local events. They are part of a larger dynamic system, a system where energy moves between worlds. And that raises a deeper question. If Dione is experiencing internal activity, even at a subtle level, then how many other moons might be doing the same, without us noticing? The possibility beneath the ice. The presence of a subsurface ocean on Dione is still under investigation. It is not as clearly confirmed as on Enceladus, but the evidence is compelling. Gravity data suggests internal differentiation. Surface features indicate past tectonic activity. Charged particle interactions hint at material exchange with the surrounding environment. Taken together, they point toward the same possibility. Liquid water may exist beneath Dione's surface, and where there is liquid water, there is potential. Not certainty, not proof, but potential. Ocean worlds are now considered some of the most promising places to search for life beyond Earth, not because they are Earth-like, but because they provide stable environments where chemistry can persist over long periods of time. Dione may not be as active as Enceladus, it may not erupt dramatically or reveal its interior easily, but that doesn't mean it is inactive. It may simply be quieter, a moon still in transition. The cracks on Dione are not the end of the story, they are a moment within it, a record of stress, pressure, and change. And if the internal forces responsible for those fractures are still active, then the surface we see today may continue to evolve, slowly, subtly, over timescales far beyond human observation. Cassini gave us a glimpse, a snapshot of Dione at a particular moment in its history. But that moment is not permanent. The moon will continue to respond to the forces acting on it, to the pull of Saturn, to the resonance with its neighboring moons, to the quiet energy building beneath its surface. The meaning of the fractures. For years, those bright lines across Dione were a mystery, unexplained features on a seemingly unremarkable moon. Now they tell a different story. A story of internal motion, of hidden heat, of a world that refused to remain completely frozen. They are not just cracks. They are evidence that even in the coldest regions of the solar system, change is still happening. The final realization: when we look at Dione now, we are not just seeing a distant moon. We are seeing a system in motion, a world shaped not by a single event, but by continuous interaction, by forces that operate slowly but never stop. And that realization extends far beyond Dione, because if a small, distant moon can remain active for billions of years, then how many other worlds are still changing, quietly, beyond our current ability to observe? The fractures on Dione are not just marks on its surface. They are reminders that the universe is not static, that even in the deepest cold, even in the farthest reaches of the solar system, there is motion, there is energy, there is change. And sometimes those changes leave behind just enough evidence for us to realize how much we still don't understand.